Um, okay, Anirudh, we are live now. So you can take it over.
Okay.
You can share screen and present.
Yeah, sure.
All right.
Just a minute. How to share? Wait,
On the Zoom, I mean, you're in the Zoom meeting, right? So you can share screen.
wait. I'm just looking for that. Share. Share screen. Okay. Okay. So can you see my notebook?
Yes.
You see my screen? Yeah.
Yes.
So I was thinking, since I have only 45 minutes, I'll allocate more time towards the Airbnb project and maybe some less time towards the other two projects. And I will describe all of them. So,
Sure.
starting off with the ML assignment. So basically,
Anirudh, maybe you can start off with your Airbnb project, and once you finish that, you can,
okay.
walk us
So
through.
you want me
Yeah.
to do that first?
Yeah.
Okay. So this is the project that I've chosen, which is Airbnb pricing prediction for different Airbnb properties in different cities and corresponding to different features. And we want to see whether the model does a good enough job of predicting the actual values. So it is a regression problem. So let me start. So I start by importing the necessary libraries. So these are the libraries like pandas, numpy, etc. Then I will read the file from the CSV. Uh, here is, and then I will display the data set. So as you can see, there are about 17 columns. The problem statement itself, oh, it's stuck. I'm not able to move the cursor. No, it's stuck. Okay. Yeah, so it keeps getting stuck in between. Actually, I'm not able to browse, scroll, or anything. Okay. So, yeah, so as you can see that this is a given data set, and we have to decide what do we want as the target variable. So as you can see here clearly, that makes the best sense to take price as the target variable and all the others as features. So we have city, we have price, we have day, we have room type, shared room, private room, person capacity, superhost, multiple rooms, business, cleanliness rating, guest satisfaction, bedroom, city center, metro distance, attraction index, normalized attraction, restaurant index, and normalized restaurant index. So these are the columns, and we'll be plotting all of these columns against the price. The shape of the data set is 41,714 rows and 19 columns. We do a df.describe, and we can see the values as the mean, standard deviation, minimum, etc. So the mean price is $260. The minimum is $34, and the maximum is $18,545. And 50% is 203, 25%, 144, and 297. So these are just statistical measures for each of the features. Then we will see, next we will look at the null values in the data set. So as you can see that right now there are no null values. So that's good. Like we can go ahead and try to do feature analysis engineering. Then we will list out the categorical features in the data set as Sorry. Sorry. Categorical features as object type. Then the numerical features, we will separate them as those which are not categorical features, and we will append them to num feeds. And as you can see, these are the numerical features: price, person capacity, cleanliness rating, guest satisfaction, city center, distance from the city center, distance from the metro, attraction index, normalized attraction, restaurant index, normalized restaurant. These are numerical features. Then I will go to univariate analysis. So here I do a histogram plot of the different numerical features. First one is price. As you can see that obviously the most of the prices fall less than 2,400, but we know, as I described previously, that there is an apartment which has 18,500, but because it's only 1 point, it's hardly seen over here, but most of the prices fall less than about $1,000. Then we have the person capacity, which is obviously it's in multiples of 0.5. So it's either, no, sorry, multiples of 1. So it's either 2 or 3 people or 4 people, 5 people, 6 people. So from 2 to 6 people, each of the apartments can hold. The cleanliness rating of the apartments mostly is 8, 9 or 10, with 9 and 10 being so they are usually very clean. The guest satisfaction is also is pretty good, between 80 to 100. And then we can see distance from the city center. So it is located, like most of them are located within 10 kilometers from the city center and located within about 2 kilometers from the metro. Then we have the attraction index, which is an index which they've calculated, and it is less than between 0 to 1,000. So that's good. Then there's a normalized attraction index, probably the normalized version of the same. Then there's a restaurant index, which probably tells you how close it is to a restaurant. I'm assuming so. It shows values between 0 to 2,000. Then there's a normalized restaurant index, which is a value between 0 and 100. Probably it's normalized between 0 and 100. So the lower the value, the better, I guess. And it's probably the distance to a restaurant. So these are the numerical features histogram plot. And again, I will print out the data set. Then I do an exploratory data analysis of, I will create bar plots for each of the categorical variables. We have the cities. So we have different cities, and we have the number of apartments in each cities. As you can see, Rome and Atlanta, Athens have a very high number of apartments, along with Lisbon, and these probably give a distribution of the number of apartments in each city. Then the weekday or weekend, how many people choose to come on weekdays or weekends. Then the number of private rooms versus standard rooms versus the home apartments, entire home apartments. So as you can see, the entire home apartments are predominant. AirBNB sites are predominantly entire home apartments, with a small number being private rooms and a very small number being shared rooms. Then we'll see categorical variables, bar plots of different categorical variables. This is the same thing as previously. Yeah. And then I will do a box plot for each of the categorical variables. For each of the numerical variables. The price, as I told you, it goes up to 18,500. So we can see this graph, but actually most of the prices fall within so the interquartile range for this box plot is hardly seen over here, because most of the values fall within that 0 to 1000 with all these as outliers. Person capacity again between 2 and 4, most of them. And then the cleanliness rating is also, as I described previously, between 9 and 10. And the guest satisfaction is also high between 90 and 100. The distance from the city center is between, say, 1 and 3 as the interquartile range. And the metro distance is also low, less than a kilometer. And we can see the interquartile range with a few outliers, high distance. Attraction index is also less than 500. Normalized attraction index and restaurant index and normalized restaurant index. Okay, so this is the block box plot, which is just the description of whatever I have described previously in the histogram. And then I will go to the numerical distribution of the with KDE showing the shape of the distribution with peaks and normal distribution and normality. So as you can see, the price peaks at below $1,000. This is the shape of the distribution. So the person capacity is mostly most of them accommodate 2 people and then or 4 people. Cleanliness rating, as you saw previously, is high. These are the peaks, and then the guest satisfaction, distance from city center. So the distance from city center normalized plot shows that it is fairly normal between 0 and 10 kilometers, showing that can be randomly distributed between 0 and 10 kilometers. And distance from the metro is also looks something like a normal plot. So between 0 and 3 kilometers. Attraction index, normalized attraction, and the restaurant index is slightly skewed towards the right. So it's not exact, it's like a half normal distribution, and so is the normalized restaurant index. Then I will go to the then I will remove the price, and these are the numerical features. And I do a count plot of shared of each of the count of I'll do of each of the category true false binary variables. So here it is a shared room. Whether it is a shared room, most of them are not. Whether it's a private, most of them are not private, not private rooms. And whether there's a superhost is also not true. Yeah, so those are the 3 binary variables. Then I'll go to the scatter plot of the different numerical features, which I've already described previously. So as you can see, person capacity, generally the price when the person capacity is more, the price also tends to increase. That's why we can see more points over here. And the person capacity is 4. There's only one outlier, which is about 12,500. The rest of them are all here. And with 2 person capacity of 2, most of them are below 2,500 with a few outliers. So that is somewhat expected, except that maybe the outliers show that maybe the property is of a very luxurious type or something. That's why it's higher priced. Then there's a cleanliness rating. Also the scatter plot, which most of them cluttered and a few outliers in price. So showing that cleanliness rating and price are correlated with each other. Then there's guest satisfaction and price. So here actually we'll see a more expected kind of scatter plot with the guest satisfaction being higher, obviously, with the higher price. So we have more points cluttered towards near 90 and between 90 and 100 with higher price. So yeah, higher the price. I mean, like greater guest satisfaction would correspond to greater price. Then distance from the city center is also expected. lesser the distance, greater is the price. Lesser is the distance from the metro, again, greater is the price. Attraction index, I assume that attraction index, the lower values are better. So because it's not like, yeah, so lower the attraction index, higher is the price again. Normalized attraction index is quite similar. And again, the restaurant index should also indicate closeness to restaurant or lower values are better. So the lower restaurant index corresponds to the higher priced properties. And then we have a normalized restaurant index, which is fairly evenly distributed with price because it's normalized. Then I will go to relationship between all the independent variables using correlation matrix. So these are the numerical variables, and this is the correlation matrix between correlation between each of the numericals. Obviously, we can't make out like because there are too many of them, but like I'll just go through maybe one or two which stand out, which are pretty high. So yeah, so distance from city center and normalized restaurant index have a correlation of about 0.38. Attraction index and normalized restaurant index also have a correlation of 0.57. And obviously normalized attraction index, normalized restaurant index also have a very high correlation, and so do the restaurant index and the normalized restaurant. So yeah, so you can see the indexes seem to have high correlation with each other because they are normalized to within 100, and generally they tend to be low. Among the other features, I can say that so price is correlated with number of bedrooms, 0.21 that you can expect, and so is correlated with the normalized restaurant index 0.22. And then there is price with uh, attraction index, which is 0.17. 0.28 cleanliness rating and superhost. So if there is a superhost, then the cleanliness rating tends to go up. So then, so that's a correlation. Then we'll do a pair plot of all the numerical attributes of features. So this is a pair plot. I mean, it's basically a scatter plot between different numerical attributes. Don't have to go through. And now I will do some data cleaning pre-processing. I want to define a function to remove outliers using Z-scope for only numerical. I will set the threshold as 3. That means 3 distributions away from the three standard deviations away from the mean. And I'll define a function, remove outliers. I remove the outliers in this df new with the argument as continuous numerical attribute, which has skewness. Then next is I will use a label encoder to encode the categorical variables. So as we can see, there are 3. City is between 0 and 8. So there are like, I think there are 9 cities. There's day is 0, 1, that means day or night. Room type is 0, 1, 2, which is shared, private, and just an apartment. So therefore, this is the true false variables, which is obviously encoded 0, 1, 1, 0. Then the shape of the new data set after removing the outliers, about 3,000 rows have been removed, 37,173 rows, and same number of columns. And we describe the new data set again, data frame. And now we will, so that is the feature selection and this thing. Now we'll move on to the actual algorithm. So separate the target variable and the feature. So I will drop price and I will set y as the price. And then I'll do a train test split of 80-20, random seed of 42. And then I will scale the values in the resulting data set. using a standard scaler. Now I will do a fitting using decision tree regressor. Sorry, this actually works, but I was doing this at the last minute, so I got some error. But so you fit the regression model, X-train and Y-train, and you should get something. And so I print so this was the earlier predicted value, but with the decision tree, so I have printed out the predicted values, and most of them are very similar, like they are not giving much variation. So I don't know whether it has done a good enough job. Uh, so 206.76, etc., the first 50 values. So maybe I should try another algorithm. So I tried the SVR, which is support vector regressor. And then I use a lasso regression model to predict on the data set. Then I will go on to the mean squared error. So these are the three models I've used. I've used the decision tree regressor, I've used the SVR, and I have used the lasso regression model to fit the data. And then I print the mean squared error for the decision tree, getting about 49,000. And this is the prediction of RFR, which is random forest. It's giving more diverse values rather than similar values, which shows that this could be pretty good indicator. But however, when I print out the white, anyways, so this is the result I'm getting. I'm not sure in terms of the closeness of the values. I don't know, because this is a regression problem. So um, there may be some issues with the algorithm, like why are they not close to each other? Because it should have been, maybe it should have been closer, but as you can see, it's not very close. So maybe some features are missing, but yeah, that is the result of my regression. Then I will go on to unsupervised learning. So with unsupervised learning, what I did is I will create a cluster. Basically, what I'm doing is I'm taking the DF, the data frame, and I am clustering it. I am using k-means clustering to see what is the optimal number of clusters, and then I plot it, and I find that the number of clusters would be about 6 or 7. Now, why I did this was actually that, like I said, if we have a number of properties, can we segment those properties based on our own criterion? And how do we name that criterion? So I don't know. So maybe like based on the given features, I found like 6 clusters partitions is appropriate. Then I look at the cluster centers for each of them. So this would be for the 19 features or so. Yeah. And then I will do perform a 2D scatter graph to see if there's any relation between guess then so that is I'm done with the regression, the supervised learning, as well as the unsupervised learning. Now I will go to scatter plot of the different variables, guest satisfaction versus price, which I've described earlier, but I'm doing it again. So higher the guest satisfaction, greater the price. Scatter plot of number of bedrooms versus price. As you can see, probably there are, it should be that more bedrooms would be higher price, but we are seeing this as equally distributed. I mean, there are a lot of outliers here, probably because, yeah, like the quality of the bedrooms is greater, so so it doesn't matter. Then scatter plot of cleanliness rating versus price. Higher the cleanliness rating, greater the price. Now the last thing is perform feature selection importance. So which features contribute most to the problem at hand? Which features contribute in determining the price? As we can see, bar plot determines that the city uh, plays a big role. So which city you're in, the number of bedrooms, obviously, normalized attraction index, person capacity, and room type. So these are like the top 5 features. I suppose city, because the same property type of property in a different city will be priced different. So that's why it's very high. And then bedrooms, yeah, greater number of bedrooms will be higher price, etc. So from the above graphs, it's clear that city has a large influence on the price of Airbnb rooms. Most important, the number of bedrooms comes a close second, as more bedrooms usually means higher price. The third is the person capacity, meaning larger rooms are probably priced higher. The normalized attraction index makes a surprising entry, as it probably indicates the attractiveness of the surrounding area, which means that potential customers look at the surrounding area attractiveness for renting a room or house. So this is my project. Um yeah, I think I'm done with Airbnb project. I have time to go through the other two, but my conclusion would be, based on this, would be that yeah, Airbnb feature selection. I mean, the determination of price of an Airbnb property with other properties is can be done. With these given features, and but I still feel that more features are required, and maybe the regression. I use pre algorithms, and I felt that it could have been better. So maybe if I tweak it a little bit, I can get better result. But that is how it is. So yeah, thank you. Um, yeah. Next, I'll move on to my visualization project. So yeah, so that was Airbnb. Next, I'll move on to my visualization project, which is an analysis and visualization using Python modules on a raw data set of my choice. So I have chosen, first I import the necessary libraries. Next, I have chosen a data set, which is the global power plant database. That means um, the power plants distributed throughout the world, and the features describing them, and visualize some of those features. So basically, so I'll read the data frame pt.read CSV. I will see the null values very high. So I see a very high number of null values in these features. So they obviously need to be removed. So we can't substitute them because as a proportion of the total number of data points, they're very high. So I will drop all of these variables. The resulting data set has 34,936 rows and 17 columns. So as you can see, these are the columns. This is the country. This is the long form of country. This is the name of the power plant. This is the GDP, IDNR, capacity in megawatts, latitude, longitude, primary fuel source, the source of the data, and some other variables, estimated generation note, etc. And then there is, yeah, so I think that's describing the data set. And of course, there's estimated generation in gigawatt hours, which is one of the primary features we'll be using. The shape of the data set is as I said, 34,936 into 17. Describe the data set with capacity. These are the four numerical attributes. So capacity in megawatts has a mean of 163 standard deviation, minimum of 1, and a maximum of 22,500. And estimated generation in gigawatt hours has a minimum of 0 and a maximum of 82,810. Then we will see all the columns in the data set. Then we will identify the category, display the categorical nominal features recognized of type object. And these are the categorical features. Display the numerical features. There are only 4 numerical features with which we'll be playing around in this data set. That's a capacity, latitude, longitude, and estimated generation. Next, we create a histogram of the numerical features. As you can see, capacity in megawatts is very low. It's between it's probably less than 1,000. So there are like most of them produce like less than 1,000 megawatts of energy, and that's why you have a very we have a peak over here. The latitude, so we see that most of them are lying to the east of the. Sorry, most of them are lying to the north in the northern hemisphere. These negative values probably indicate Australia and New Zealand. And then longitude, yeah, most of them are some. I mean, they are equally distributed between west and east. So there's countries in the east and there's countries in the west. And estimated generation in gigawatt hours, which is quite similar with the capacity in megawatt in terms of the distribution. That means most of them below a certain value. As we'll see later, that they are related to each other. They can be related in some way. So next, I'll go to the skew of the numerical features. So df final.skew, this is the skewed values. The null or any values in the data set by column. So these are the null. I will use a simple imputer with the median for every column. So I will fill out the missing values with the median, and for each of these 4 numerical features. And yeah, so the method I use is drop the numerical features and concatenate them to the data frame with imputed values, which seems to work better for some reason to get the original data set with the imputation. So this is the data set with the imputed values. Now again, I'll display the null NaN values in the data set. So, and then because these are all categorical features, I will have to remove them. So I remove the null values, and finally the resulting data set has no null values. Then I create a displot of the numerical features. So this is capacity in megawatts, this is latitude, this is longitude, and this is estimated generation. As we see, longitude and latitude are normally distributed, with longitude having 3 normal distributions in one plot, which correspond to probably 3 regions in the globe where more countries are lying. Univariate analysis of numerical features using the box plot. So I'll do a univariate analysis, and I find that because most of the countries, we focus more on this estimated generation and the capacity. Most of the countries produce less than 1,000 megawatts. There are it can barely be seen, but the highest producer is greater than 80,000. So that is an outlier here. Similarly, for capacity, the highest producer is greater than 20,000. There are many outliers, but the interquartile range is probably within 1,000. So that's why we cannot see the box plot clearly. Then IQR is equal to Q3 minus Q1. So yeah, IQR is Q3 minus. So this gives the interquartile range for capacity, latitude, longitude, and estimated generation. Then we further reduce outliers by considering only 1.5 times IQR on interquartile range on both sides. So this is the shape of the clean DF. Then Then I'll do a box plot of the individual features, which is what I've shown previously. Except that I'll be showing it individually. This is capacity in megawatts, latitude, which could not be seen earlier because it was overshadowed by high values. It can be seen that between say 30 and 50 north latitude, most of the countries are lying. Then longitude also between -75 to 50. That means the west and the east, obviously. And 0 is, of course, the central meridian, where most of the countries are lying. Then I will do a box plot of estimated generation. As I said, since the highest value is about 80,000 and most of the values are within 1,000, we cannot see the blue box plot over here because the IQR is very small compared to these very high values. Then I will do a correlation between the different features. There are 4 features. As you can see from this, there's only one correlation which is of interest, and that is estimated generation versus and capacity in megawatts, which has a correlation of about 0.95. Then I do a pair plot. I do a pair plot of the 4 numerical features. Then I will go to the country list. So we identify the top 5 countries based on count. So USA, China, Great Britain, Brazil, and France are the top 5 countries. We will we plot what are the energy sources for the top. So these are the queries that I'm supposed to make. What are the energy sources for the top 5 countries by count and their distribution with color coding? So the top 5 countries are this, and the distribution of energy sources within each of those countries. I'll do a count plot of the same. Hydroelectric power is high in Brazil. China has probably a high amount, produces a lot of coal power. France also produces coal power. Great Britain produces coal power, and USA also produces coal power. I think, and China also produces quite a lot of hydroelectric power. And solar power is quite high in the US and Great Britain. Yeah, and then I do a displot of the same, and I find that yeah, USA produces very high coal power. Great Britain comes second, and probably China third. And yeah, there's oil and nuclear energy, which is also one of the sources. Solar energy is another one which we have to consider. Then I'll do a scatter plot of estimated generation of power and capacity. As we can see, the plot is almost linear, suggesting an almost linear relationship. So this is a primary relationship, and capacity and megawatts and estimated the generation in 2017 are nearly linear. It means they are linearly related to each other. Next, I will go on to the hypothesis testing. So in hypothesis testing, what I do is first I will plot a KD plot of capacity and estimated generation, and this is the plot. And I'll find out the mean value for capacity versus estimated generation, the capacity of each of the power plants and the estimated generation. And these are the values I get. I print the ratio of the means, which is 4.195. So my hypothesis for this is that that they are linearly related to each other, or they are correlated with each other. That is my hypothesis. So how I go about is by doing an ANOVA test. So basically, I will import the F1-way ANOVA test, and I will multiply the megawatts with the ratio which I calculated previously and the estimated generation, and I will do a one-way ANOVA test and see the p-value. Now, the p-value is so high, it is 1.0. It is very clear that we cannot reject the null hypothesis that estimated generation of power is proportional to capacity of power in megawatts, which means that they're most probably related to each other. Then we do a t-test of the same to verify that results, and we get again a very high value of 1, which verifies the previous. Next, I will go on to the second hypothesis, which is that a t-test between capacity and megawatt, to say that hypothesis that the capacity in megawatts is equal to the estimated generation. And we'll do a paired t-test, and we get a 0.0 p-value, which means that they are not related to each other. They are not equal to each other. Then we take, I do another t-test where I say that the capacity in megawatts is greater than the estimated generation, and the p-value is again very high. So we cannot say that they are equal to each other. Since the p-values are so high for both cases, we cannot say that capacity is greater than or cannot say that the capacity is greater than or less than the estimated generation, therefore must be proportionate. The must be proportionate as we are multiplying by the ratio factor to test for equality. So if so the first hypothesis states that they are correlated, which means that if we multiply megawatt by the ratio factor, they will be equal. But if we test the equality of the two, which is the second hypothesis testing, we find they are not equal to each other. So that is the result. Next, I will group by estimated country dot sum sort values. I will group by country, and I will create another data frame where I'll group by latitude and longitude. Then I will do a bar plot of the generation of power from each of these countries. So China has the highest estimated generation. USA is second, India is third, Japan is fourth, Russia is 5. So these are the countries which had the highest estimated generation of power in the year 2017. Which countries have the highest capacity in megawatts for generating power? China, USA, India, Japan, and Russia. I have taken 2017, but I think that the results from here can be extended to 2018, 19, 20, 21, 22, because the pattern, this thing will be quite similar. The distributions will be quite similar. Next, I will go to the third query, and I will show you that the distribution of each of the power sources, the capacity in megawatts. So the primary fuel sources and what is their capacity. So obviously coal has produces the greatest amount of power, has the greatest capacity in megawatt. Then is gas, then is hydroelectric, then nuclear, then oil, wind, solar, and biomass. Then I go to the fourth query, which is I group by name, and I will try to display the top 10 power plants. Sorry, the top 10 power plants for estimated generation. The names of the top 10 power plants which produce the greatest amount of power, which have the greatest estimated generation. So these are the names: Kashizawa, Kariwa, Baitan Dam, Tapu Binochi Dam, which probably rise in China, I'm guessing. So I'll have to correlate that with data, but most probably in China. So I suppose that for singular sources of power, most of them, the highest sources lie in China. Then the last query is the histogram plot of all the numerical features. So capacity, as you can see, capacity in megawatt is between 0 and 0.4 into 10 power 6. And there's one outlier. There are a few outliers over here, but most of them lie within 0.4 into 10 power 6. Then I will do a histogram plot of estimated generation in gigawatt hours. Again, as you can see, it's similar to the previous. Most of them are within 1.5, and there are a few outliers of 5. From the above two plots, we can see that the estimated generation and capacity in megawatts has a low tail distribution, which means most of the countries produce less power, with few of them on the upper tail producing 5 or even 6 times of that. These would indicate the big 5 countries mentioned earlier. Then I will histogram plot of the latitude as well as the longitude. The 3 peaks suggest there are many countries in the middle 0 latitude near London, many in the extreme eastern region and the western region. So that is my visualization project, which is the estimated generation of power and capacity in megawatts for different power plants throughout the world. Next, I will move on to my classification assignment, which is the final. So this one, I import all the necessary libraries, and then I read the data pd.read signature.csv, print the top 10 rows, and describe the data set. The data set has a mean of 218 with a minimum value of 0 and a maximum value of 57,715. Hello, Ashwin. Hello.
Yes, Anirudh, I'm still here.
Okay. Yeah, it's just checking. Okay.
Uh, yeah, you can quickly browse through this notebook.
Yeah. I'm almost done.
Okay.
So, yeah, so this is, so has a mean of 218, minimum of 0 and a maximum of 57,000. And then, of course, there are other, these are all other like technical features in the data set. The shape of the data set, 22,544 rows, 40 columns. These are the columns. And display the different classes. There are 2 classes, which is anomaly and normal. So we basically we want to classify whether given entry whether a given row is an anomaly or normal. It's basically anomaly detection of certain different rows. So yeah, then start doing bivariate analysis by plotting each categorical feature and color coding the target variable. So there's anomaly, and so the protocol type, TCP, TCP/MP, and UDP, and what are the different anomaly? What is the count of anomalous versus normal class for each of them? Then we have service, we have flag, root shell. So root shell has almost equal number of anomaly and normal for the 2 types, 0 and 1. And when logged in, and so when the person is not logged in, the chances for anomaly are higher. When the person is logged in, is more likely to be normal. So then we do another bivariate analysis of categorical features versus as being anomal or normal target variables. The protocol type, TCP, UDP, which is kind of similar to the previous one, except that, yeah, it's kind of similar, except that we have the anomaly and the normal adding up to 1. What is the percentage of values for each of them? And yeah, that's similar to the previous. So these are all technical protocol types, service flag, root shell, and in logged in. So when he is logged in, then there is a lower chance of anomaly. When he is logged out, then there's a higher chance of anomaly. Then I'll plot a box plot of each of the numerical features and observe for outliers if they are present along with Q1 and Q3. So this is a box plot for each of the numerical features. Most of them are error rates, host error rates, etc. Please note if plot most, if not all of the variables have many data points more than Q3 values, showing there is some skew in the data set. Yeah, there is some skew with respect to the host error rate and the differential server rate, etc. So there is definitely some skew because many outliers present. Then I will plot a histogram along the KD plot for each of the numerical and observe the distribution. So this is the KD plot and numerical distribution of the same. Is observed that very few of them have normal distribution and most of them have values cluttered at the bottom end of the spectrum, indicating that it's not as that is not a random distribution and error rates generally tend to be small. Yeah, so yeah, this is one observation I made, that very few of them are on the lower end of the spectrum, showing that error rate because most of them are some kind of error, so its error rates are generally tend to be small. Then I plot a scatter plot of x variables as the DST host error and y variable as DST host server error rate, which are again two numerical attributes, and we find an almost linear plot. So we find a linear plot, and then there are other points which are scattered everywhere else. And on the linear plot, we find that they are anomalous. That means, yeah, so the error rates are highly correlated with each other when there is an anomaly. Whereas when there is no anomaly, then they are not correlated. So next I observe for null values in the data set. And there are only like two columns, one with 18 and one with 13. Use a simple imputer library to impute the null values with the median of the distribution. And so I impute the null values. And we find that now there are no null values here. Yeah, no null values. Next, I'll define a function to remove outliers using z-score for only numerical attributes, and I set the threshold as 3.5. So if the point is 3.5, because I had tried with 3 distributions from the normal, and I find that a lot of points, more than 20% are removed. So I will put the threshold a little bit higher as 3.5, and then I will remove outliers which are greater than 3.5 normal this thing from the mean. So I remove the outliers, and this is the new data set with 20,719 rows and 40 columns. I do a correlation heat map. There are too many. There are too many features, and it wouldn't make sense. But from what I can see, actually, that a lot of them are. So the lighter it is, means the higher the correlation. And we can see that besides this diagonal, there are some correlated features here, and they would indicate that the error rates are correlated with each other. So there's a high correlation between error rates, and as I showed you earlier, when there is an anomaly in the signal. So then I do a label encoding of the object data type. Label encoding. So these are the 1, 2, 3, 4, 5 different features. Logged in is 0, 1, root shell is 0, 1 again. Binary flag is these many, and service is these many. And then I will fit the label encoder with the and for column, with the new data, and create a new data set. And then I will describe the new data set after doing the label encoder. And I will drop next. Yeah, so this would be the feature engineer. Next, I will move on to the fitting the classifier. I separate the target variable as y and the feature variable as x. So x is, I drop the class, and y is the class. I do a train test split of 80-20. And I will fit the different algorithm: logistic regression, decision tree classifier, random forest, neighbors classifier, SVC, multinomial naive Bayes, and add a boost. And I will see the accuracy score for each of them. Logistic regression gives about 82%, decision tree 98. Uh, RF, which is random forest, has the highest accuracy of 98. KNN is 96, and SVCNB and add a boost also gives a 96%. And then I will do a cross validation. By taking 10 cross validations and computing the average results of all the 10 by taking, this is called tenfold cross validation. We can perform as many fold as we want and choose CV appropriately for this. So I choose CV as 10 and do a cross validation. Again, random forest gives the highest, decision tree gives the second, add a boost gives pretty high at 96% accuracy, and yeah, and so does KNN classifier. Then I do a hyperparameter tuning where I set different values for criterion: max depth, number of estimators, minimum sample, max features, and random state. And yeah, this actually takes a while. Took me about 3 hours to get the best parameters and yeah, for this model. And using these best parameters, again, I will fit the model, and I find the accuracy is about 98.43 for the RF, which is the random forest classifier. Print a few of the columns of them of the Y test. Then I will do a classification report, the confusion matrix. So the confusion matrix basically gives 2,260 correctly true, which is true, 1,819 false, which is false, 26 and 39, which are misclassified. So, I mean, like you can say approximately 4,000 out of maybe 4,050, and 4,000 are correctly classified and about 60 are misclassified. So that's pretty good. As we saw, we got a 98% accuracy. And then there's a classification report with high precision, high recall, and high accuracy also. So that's pretty good. Yeah, it's a good result. And then of course, evaluate the model. We perform feature selection importance, which is the importance of the different features and how they contribute to the target variable. So the top 10 features are DST byte, SRC, host, differential server rate, flag, service, DST host, error rate, DST host, SRV count, DST host, SRV, error rate, and duration. Yeah, I suppose most of these are technical, but I guess since there are so many error rates here, I can say that probably the error rate being high would indicate that there is an anomaly in that signature or in that signal. So that is why, and also the DST bytes and SRC bytes, meaning that if those values are going here on either side, it would indicate an anomaly. So that would give the top 10 feature importance for each of the attributes after performing the classification with different classifiers. So yeah, that's my classification assignment. Thank you. And I think I've covered all the three. So the first was AirBNB, then visualization project, and then my classification assignment. If you have any questions, please feel free to ping me or comment. Thanks. Ashwin?